So today we're going to continue on with the last part of our IUPAC naming and get into molecular bonding. So this is where we're going to start to transition from just naming things and a particular line bond structure to start talking about how bonds are formed and their representation. This is also talking about things like orbitals. This is how we talk about where electrons are localized and then start to describe how reactions occur. Now, if you remember last time, we introduced this general pattern IUPAC for naming things. This is a sequential, systematic way to name molecules as drawn. Remember, the word that you get, the actual name, has this sort of form where up front of the word is our substituent. The substituent describes the stuff decorating the main chain of the molecule. That's what we refer to as our root, infix, suffix. The last part of the molecule is the descriptor that sort of talks about the family class or other pieces of the molecule specific to that specific longest carbon chain. The suffix is the most important because this is what we call, or it's sort of linked to what we call the functional group. The functional group gets a special priority not just because it modifies the end of the molecule, but it helps us to put common types of molecules together with common functional groups because they have common reactivity, common properties. Anything else in that sort of capacity is really what we are focused on. So it modifies the end of the name, and what that also means is things like numbering are going to be prioritized according to that piece of it as well. We left off last time introducing this concept of alkyl branches. Alkyl branches are different depending on the number of carbons in their chain. They follow the same pattern as our longest carbon chain part. The one thing that is different or unique is we have these, what we call commonly derived or common names. They don't follow the IUPAC category. They're not just named based on number of carbons in their longest chain. Think of it as a group of carbons changing depending on how they're attached to the chain. So the ones here, butyl, 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 these are three, actually including this one, these are four different permutations for how you can have a 4-carbon branch. So there's still 4 carbon branches. They're all called butyl, but depending on how those 4 carbons are arranged, we have different isomers associated with them. They get a special name accordingly. We're going to go through an example that talks through this part here. The only other one is propyl. There are 2 ways of arranging a 3-carbon branch as a side chain. So you do need to know these and the differences between them. Again, the presentation we're showing you is this part. Some of this naming, calling it like a sec butyl or a tert butyl, comes from this concept of what we call sort of multiplicity or substitution pattern at a carbon. So what we have is this point here where we refer to carbons in their class depending on what is attaching to them. Think of it this way. It is the number of carbons, not hydrogens, attaching to a carbon. So what we call a primary carbon means it is a carbon with 1 carbon neighbor, 3 hydrogens. A secondary carbon has 2 carbon neighbors, meaning how many hydrogens? If I have 2 carbon neighbors, I have to have 2 hydrogens. The implicit hydrogen rule is applying to this part too. That's why this guy here is referred to as tertiary because it has 1, 2, 3 carbon neighbors. How many hydrogens? 1. What would you call a carbon that has 4 carbon neighbors? Basing on this, you would expect that to be called, quaternary, quat centers. So this multiplicity, this idea allows, again, this is a way of looking at a molecule. If I have my hands behind the back and I say, for this one here on the screen, how many primary carbons does this molecule have? So altogether, there are how many? There are 3. There are 3 primary carbons. What I mean is, in this entire molecule, we have 1, 2, 3 carbons that have only 1 carbon neighbor. Likewise, there are how many tertiary carbons in this molecule? There are only 1. The guys in the middle, the CH2 ones along the backbone, those are secondary. So this is partly where this naming convention comes through. So, look at this for a second. Take a second to look at this one. What's the longest carbon chain in this molecule? Okay, now that you've got a thing in your mind, turn to the person next to you, convince them why you are right or why you're possibly off between two. Come up with one answer. Okay, so consensus on 3. There are how many carbons? A, B, C, D. This is B. That's right. There are 8 carbons in the chain. Now remember, when you're counting longest carbon chain, you do not go through the process. We do not sit there and go, okay, how many carbons in the longest chain? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We do not skip over. We count contiguously along the carbon backbone. So you basically think of it like you're walking through a maze. If you hit the end of a chain, that is the direction you've gone. You may have gone the wrong direction. You can't back up and sort of go different parts of it. But you can start on any particular carbon chain. It also doesn't have to be just oriented left and right. If I just went through here, 1, 2, 3, 4, 5, 6, 7, that doesn't mean that there's another long chain that doesn't follow this left to right or up and down kind of axis. You have to sort of count through the different parts of the structure. So for this one, I could count this as 1, 2, 3, 4, 5, 6, 7, 8. That's 1. Does anybody see this one as well? 1, 2, 3, 4, 5, 6, 7, 8. So you have 2 possible longest carbon chains. But I would argue there is a better and a worse choice. Now neither, if you were to use and name either of those 2 particular ones, they're both 8 carbon chains. If you used either of them as calling this octane, you'd be correct. But who would vote for green and who would vote for red? So green, red, okay, Maverick. Why might green be better? Yeah. Lower numbers, that's one part, maybe. There's another way too. What do you mean? On the grain. Yeah, there's a methyl group. Remember, if we follow, yeah, sorry, go for it.
I was thinking red, because if you do red, you'll have like 2 substituents, versus if you do green, you'll have 3.
Okay, yeah, and all of these are reasonable ways to sort of think about it. One option, if we follow the red path, this is what we call our main chain. Anything outside of that, this is your group, this is your branch. Things off that are your branches defined. So one of them might be, okay, you only have 2 branches. Lower branches, maybe that's better. How would you call this as a branch? What is that? 2 carbons as a branch is called a? All right. What about this as a branch? What is that? So how many carbons in the branch, first of all? 4. So it is what type of a branch? It's now in the family of, it's a butyl, but is it just a normal butyl? This could be called an isobutyl, right? Or a sec-butyl potentially. It depends on how it's attached. That's where you would have to go back to your chain here. It actually follows this pattern here. Main chain that goes to a secondary carbon that has a methyl and an ethyl substituent. So let me draw that out again. You have attaching point where I have a methyl going this way and an ethyl going that way. That is known as a sec-butyl. Okay, so that's appropriate. You could say I have some octane that has an ethyl group and a sec-butyl group. Generally, though, if you have a choice, you can also, if we went the other way, I'm going to go for the green path now. If we go the green path, I'm picking this is my main chain, right? That makes my side chain this, this, and this. What are those 3? So this one is called a, this is called a propyl, this is a, that is easy. I don't have to invoke anything else. Now again, I'm not saying either is right, wrong, better. They're both appropriate. In this case, the longest carbon chain is still 8 carbons. One of the conventions, though, could be if you can find a way to have simpler side chains, save yourself the trouble, go for that of the 2. So the naming of this one could potentially be called 5-ethyl, 3-methyl, 4-propyl. That's along this green sort of chain being your main chain. Now, if you chose to go the other way, you'd have to use the appropriate iso or sec or tert kind of a point. And sometimes you can't get around it. Like, there's not always a choice. I'm just giving the point that there may be some ambiguity here, and you can choose depending on, you can make your life easier by choosing the right sort of carbon chain in the middle. So, what is that dot? What is the substitution of this particular one? Primary, secondary, or tertiary? This is a tertiary carbon. Yes, that's right. How many tertiary carbons in this guy? There are 3, yeah. Remember, you're looking for things where 3 lines intersect, 3 carbon substituents around the outside. So, when we start to cross over now, and this is where the identity of the molecule will change, the very last part, the suffix of your name changes, it's because of the functional group. The functional group can be identified by looking at your molecule and sort of think about it, breaking it up. Don't look at necessarily as the entire molecule in like all the different pieces at once. That's like looking at the whole forest. Focus in on the trees. Focus on the component parts of it. So one way to look at this, so first of all, does anybody know what this molecule is? Any guesses?
End with an oleic acid.
Sorry, what?
End with an oleic acid.
No, I don't know if it has a common name in that point. Do you know what this group here is? This NH2 is called a amine. This is called a carboxylic acid. Molecules that have both an amine and a carboxylic acid are specially called amino acids. They're the building blocks of proteins. This is phenylalanine. It's one of our common 20 amino acids. So the way you can look at these is according to their pieces. What makes phenylalanine is its side chain, its aromatic group. So this would be called what kind of functional group? Special stop sign, circle of power. This is a benzene or aromatic. Yeah, an aromatic part of the molecule. That we said is a amine, right? This is a carboxylic acid. Those are the constituent or component parts. Yes?
So if your acid this contains alcohol, which is the OH, can the carboxylic acid count as a functional group?
Really good question. So the question is, the answer is no. You have to pick one. And this comes down to priorities. So basically, if you look at your actual function group tables, the question is, if I look at this, this is a carboxylic acid. It is a compound function group made up of things that you may have seen before. So let's quickly do a quick review. If I had carbon chain, which I'm going to refer to as R, a double bonded oxygen, and a hydrogen, what is that specially called? That is a carbon one side, C double bonded O, and hydrogen, that is a aldehyde. Yes. If I change this hydrogen to a carbon, this is now called a, no, not ester, ketone. That's right. This is a ketone now. If I take this carbon and I break it and I put an OH there, what is this now called? So the naming that you get for these functional groups are aggregate properties. Yes, it kind of has an alcohol. Yes, it kind of has the C double bonded O. It is not a ketone alcohol. It is a carboxylic acid. Its properties are because of that unit arrangement of those terms. So there are indivisible pieces. So when you have, and that's where if you go back to your point, as we talk through these specific functional groups, there's a specific arrangement of atoms which defines it as that function group. All must be present. Okay? So a carbonyl specifically is this functional group in the middle, this piece of it. But this carbonyl with a carbon one side and a carbon on the other side, ketone. If it's carbon hydrogen, aldehyde. Carbon OH, carboxylic acid. What if I did that last change? I'm going to now switch this. So yeah, this is how what I did to sort of learn these parts through. When I was learning this point, think of it like a promotion strategy. If I start off, it's only carbons, we call this what? This is hydrocarbon or alkane, right? If I take this and I put an OH there now, swap in, this is now a alcohol. Great. If I now say instead of carbon, single bond oxygen, remember there are 2 hydrogen associated. If I now promote that, where I'm going to make this a double bond, This is now, so this is my alcohol. This is my aldehyde. And that's where al helps you remember through it. If I take this hydrogen, I'm going to now add it to a carbon. I'm going to turn it to something else where now it's carbons on both of those. This is we call a ketone. If we keep doing this progression and we sort of block by block substitute that group with other things, OH, OR, NH, those kind of permutations, it's like playing Lego. Each of them gets a new identity as we do these substitutions, and you build up. One goes higher to the next, and they have a name associated with each. So the best way to learn these parts through is look at the function group table we provide, starting in that middle, working up to the top. Look at the functional groups that are there, and actually promote through. So if you have a molecule like this, how many functional groups, going back to the table we provided, that long one, the ranked list, what do you recognize here? So give me one. Halide, yeah, I see a halide. This is like playing molecular, or not Jeopardy. This is molecular Wheel of Fortune, right? So halide, direct me to, what's the halide here? Yeah, we've got a chloro, what else? Bromo and? There we go. Those are my halides. What else? What else do you have here? Yeah. You have an ester. Right here is an ester. It's an ester not because of the C double bonded O. You'd have to go more. It's a C double bonded O with an oxygen. More importantly, on either side, flanking out. So going out to the entire species. This is called an ester because it has double bond, carbon here, oxygen, out to carbon, out to carbon. It's this entire unit here that gives it that ester personality. Yes?
Is there a carbon in the middle of that? Like where that double bond and the single bond is?
Right here? Yes, absolutely. Every time you have lines intersecting with no atom put into place, there is a carbon. So that is my ester function. Okay, what else? There are two other functional groups you should pick up. What else we got? Methyl, okay. That's more like a side chain. We are like think of it this way. If it modifies the front of the name, not the back of the name, that's just fruit. That's substituents. So yeah, it has methyl groups, not a functional group necessarily. What else we got? Something that would modify the end of the name.
They have an alkene and an alkyne.
There you go. Alkene and alkyne. Those are the infix part of this molecule here. So that is how you should sort of look at this entire piece. The halogens, those are decoration parts. It becomes this part. We separate them as function groups, not methyl necessarily, because they really change the personality of the molecule. Alkynes, alkenes, yes, for sure. The ester is the one that will take you a little bit of time to see because it's not a carboxylic acid, not because we have an O carbon, not an OH. So again, this goes back to our overall list. As we work through this list, walking through the specific function groups that are present here, the naming associated, it's that pattern that we'll go through. We're going to continue practicing this as we go through different parts, but if this, on this list, give me one of these that really bothers you in order to sort of pick it. Yeah. Esters.
The ones that look like a mustache with an O.
A mustache with an O in the middle? Like here?
No, at the bottom, below the hydrocarbon.
Oh, ethers.
Oh yeah, ether. Sorry.
Okay, mustache.
No, like on the assignment, it's like a. You know what I mean?
Okay, you know what? You do you, man. That's totally fine. So again, let's talk ethers for just a second. Here's my hydrocarbon. Promoting this up to a alcohol, we would go O hydrogen. That is my alcohol. What is the next thing we could do to turn this into our mustache? What would I have to change about this drawing to make it into my ether? Add something where? Right here. I don't have to change any other part of this molecule. I just go O instead of hydrogen, any other carbon where that carbon cannot be. So this, I agree, this is an ether, right? What would it be if I do this, though? Not just carbon, but carbon with a double bond oxygen, not an ether. This is now a, and that's where the wording kind of comes together. Ethers are oxygen carbons. Esters have this carbonyl next to it. So here, back to this one, because we're getting close to it, this would be what kind of ether? If I use the colloquial name, we have two methyl groups. This could be called di-what ether? Yeah, dimethyl ether might be a way to put it on. How many lone pairs do we have on this molecule? There are two, right? So if we have this, again, if I had this, what might you call this? What kind of ether? Just generally, if we had things that go on a ring, what do we add to the name of this? It's a cyclic ether, a cycloether might be the part of it. But these lone pairs, they extend out into space like this. So this specifically is our ether bunny. Because of the rabbit ears. And you will never forget your ethers anymore. Yes?
Previously, when we were looking at the other identifying the functional groups, is that like, sorry, is like this part, is
Yep.
that a cycloester?
No, that one, so we don't have to go that far. Sorry, no, I was just trying to go back, what was a cyclic called? As far as naming a functional group, this guy here, you could stop at it is an ether. It has the root property where it is an oxygen with two carbons, not carbonyls, on either side. Perfect. So, practicing through what these are and identifying them is just, this is literally that point. It's practice. So let's work through an actual naming point. What do you call this by IUPAC? Remember, structure and strategy, first thing we're going to do, find the longest carbon chain. So, give me a number. What is the longest carbon chain in this molecule? So we got 1, 2, 3, 4, 5. If I just go left to right, if I start up here at the top, 1, 2, 3, 4, 5, 6, I could potentially do this. Is that a good choice for my longest carbon chain?
I'd go one more.
Yeah, I'd go one. Why is this a problem?
We want the substitution groups being the lowest.
Well, not just being the lowest. Remember, if I circle it this way, what I'm saying, the implicit thing I'm saying here is everything else is a branch. I can name this branch, right? That is two carbons as a branch. That's called a ethyl. If I do one carbon with a fluorine as a branch, what do I call that? Blah, 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 blah. That gets harder to do because you're now binning a group, a fluoro, into a branch. So it's like this recursive naming. It's not just a methyl. It's a fluoromethyl. It's a 1-fluoromethyl. Don't do that to yourself. The easier option is we're going to choose as a carbon substituent the carbon backbone that's still the longest. 1, 2, 3, 4, 5, 6. So this is hex, right? It's not just hex. What's the infix? Are there any double bonds? Carbon-carbon double bonds. So it's a hexane. Right. This is some hexane. It has 3 substituents on here. We have a carbon, a fluorine, and 2 carbons. So what are the 3 substituents we have? We have a fluoro, we have a methyl, and we have a right. So where are they? Where should I start numbering this if I would go this part out? So numbering goes to, yeah, this here I'd say is number 1. So it's a 1-fluoro, 2-methyl, and 3-ethyl, right? Now again, I'm not doing this by alphabetization right now. I'm just throwing them down that the numbering that associates with each one of the functional groups will have this kind of pattern. Then we alphabetize. That's where we would resort these numbers, or these here. So it should be what goes first. Alphabetically, this would be 3-ethyl, 1-fluoro, 2-methyl, right? Hexane. Oh, wow, that sucked. Hold on a second. Boop. Let me erase all that. So, 6-carbon chain. It's a hexane. More importantly, it's not just any hexane. Oh, come on. Boop. Stop it, stop it. That's my finger, not the thing. You know what? I'm going to... Come on, you. Nope. Clear all markings. Woo. Back to the pen. Sorry. So there you go. You have your fluoro, you have your methyl, and you have your ethyl. Yes?
Why don't you have a suffix for this one? Like the highest priority functional groups.
So we do. The highest priority functional group for this, go back to our table, is the alkane. So it is a hexane. If you go back to your list, halogens rank below your alkanes. So the halogen is put into the category of I am a substituent. I go out front. The main chain molecule, the suffix, is hexane. That's the parent compound we have here.
Wait, where? So alkanes aren't on the chart. Where?
Hydrocarbons.
Oh, okay.
All right. So that's how we get our particular naming numbering. Again, this is one of those points where your choice of the longest carbon chain can influence the difficulty of naming this. If we were to happen to choose the methyl group as our main chain, it would make it much harder. Okay, what about this? How would I call this guy?
Regarding the previous, like, does it matter what order you put the methyl and ethyl? Like, can you move it from 1 floral to methyl, 3 ethyl?
Oh, so like rearranging these? Yes. So as a note, what you'll notice on some of the naming assessment, alphabetization is the lowest of them, and we have some of those cases where the answers on the assessment, we don't worry too much about alphabetization. The reason why, if I told you this was a 3-ethyl, 1-fluoro, 2-methylhexane, you all would draw that structure. What if I called it a 1-fluoro, 2-methyl, 3-ethyl? Would you arrive at the same structure? Then it's okay. So we will accept errors in alphabetization, but not numbering. It is not okay to call this a 1-fluoro, 2-ethyl, 3-methyl. That is a physically different molecule. But if you were to invert your alphabetization, keeping your numbering consistent with your point, that is an acceptable answer. Okay, so this guy, what's your longest carbon chain? 5, that's right. Longest parent carbon chain here is 5 carbons. 1, 2, 3, 4, 5. You can choose any point. Most important, though, what is your functional group? What's changing the end of this molecule in this case? This is the amine, right? So the root of the chain is going to change because of that amine. So if we had a choice, this group had better be directly attached to your main chain. What does that mean about numbering? What is the number of your amine in this case? Does it matter in this case, left or right? No. Well, no, in this case, if I manage to go from the left or from the right, it's right in the middle, it's still a 3, yes.
Well, I thought you'd want to go from the left, so the substituent group of the methyl is lower.
True. That's, you blew my punchline. Numbering left to right does not change the number of the amine. It's still going to be 3 either way. But there's still a right answer. If I were to number 1, 2, 3 versus 1, 2, 3, red is still correct because why? Yeah, your other substituent, like basically what I'm saying is, the numbering cannot suddenly be decided just by where that amine goes. It's going to be a 3 amine either way. If we suddenly, the priority goes, I can't make a decision, left or right, what's the correct numbering? It will defer to the next thing down the line. In this case, the methyl group is the one that holds the ball and helps to break the tie. The reason I point this out is because this is the common sense you apply as you go through it. Priority starts at longest carbon chain. It holds the biggest ball. If you can't decide based on longest carbon chain, you move to the next category. Which long carbon chain will give you easier substituents and contain your functional group? Once you've got that, your numbering comes in. Your numbering must prioritize your functional group. But if you have a tie, left and right, it now moves down to the substituents outside. Your methyl becomes your tiebreaker. So you continue to move down the line of who has that priority depending on the circumstance. So your tiebreaker may change. This is a pentane. It's not just a pentane, though. It's called a penta what now? Yeah, pentanamine. It's not just a pentanamine, it's a what? It's a 3-pentanamine or a pentan-3-amine. Either of those conventions are correct. Like what you'll notice is we must apply a number to say where this amine is. It's on the third carbon. You could either call it 3-pentanamine out front or pentan-3-amine, the breaking that two. Like again, what you'll see is either of these two pieces. Methyl becomes here. So one of the ways to call this would be 2-methyl-3-pentanamine or 2-methyl-3-pentanamine. That designation out front of the root chain or embedded into it is correct in both cases. Use which one you find that is most available. I find this harder to say, so I will generally, if it's just pentanamine, that 3 gets promoted in between your methyl and your root chain. But that's up to you to decide. There can be cases, though, where this gets really difficult. What if we had a double bond in here? Instead of just being a pentanamine, let's say we had something that looked like, let's see if I can do this. So I'm going to draw what we had before, NH2 methyl, but I'm now going to do this also. No, I don't want to do that. That's much worse. Let's do this. Bloop. Okay, longest carbon chain is still, so it's still pent. It's not a pentane anymore. It's now a it's a pentene, right? But it's not just a pentene. This is a pentene amine. The infix changes accordingly. So this would now be a pentene amine. And it's not just a pentenamine. Where is the ene? Where is the amine? Ene is on carbon, it starts on carbon what?
1.
Carbon 1. Amine starts on carbon. So this would be better written as pent, whoops, nope, not like that. Pent 1 ene, whoops, sorry, let me go by hyphens. Hyphen ene hyphen 3 hyphen amine. So in certain cases, those numbering go along, they follow with the type of function group and the position you're talking about. We're not done yet. What else do I need? It's not just pent 1, 3-amine, it's a 2-methyl. Yeah, we need one more into this too. So we would have 2-methyl, pent 1, blah, 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 right? Yeah. Say that again? So again, look on your table. If you remember on the table, what has priority? Amines or alkenes, alkanes, hydrocarbons? The amine. The amine wins, and that's going to be the main sort of designation of this. Yes?
So when do we not have to put the 1 in?
You must put the 1 in if there's any ambiguity. The double bond here could be anywhere between any two carbons, right? If we had something like a carboxylic acid, the chain starts with the carboxylic acid. That will always be carbon 1. So on that point too, we have 3 functional groups where the 1 is not necessary. It's redundant. So what I'm going to tell you is carboxylic acid. Give me another 2. What are other 2 functional groups based on the table that we've got? Let me go back to that. What I'm saying is it has to be a functional group that has to be something carbon 1. On this list, what do we got? Oh, poop, not that. Nope, nope. There we go. So these are things that you call like chain starters. That has to be carbon 1. Okay, ketone. Could you have a ketone in the middle of a carbon chain? Yes. Could it be at the end of a carbon chain? No, because if it's at the end of a carbon chain, it's now called a... Yeah, remember, if you start a carbon chain with a carbon double bonded oxygen, that means one side's carbon, the other side is hydrogen. So aldehyde is a carbon 1. So we have aldehydes, we'll start chains. We have carboxylic acids, we'll start chains. Give me one more. What's that? Nitrile. Bam, yes. Carbon here, what we're showing you is, if it starts or has a carbon, which only goes off, the carbon chain extends in one direction only, these become single units. They become only that point. Those are your classic ones that you're going to see where you don't need to have the number associated with it. Oops, wrong way. Okay. So, back to this too. Functional groups are so important though. It can fundamentally change things like counting. Yes?
So could you have a molecule that had like a carboxylic acid and a nitrile, and then would you just assume whichever one was like the suffix would be the one, and then the other one would be the N?
So really good question. If you had a molecule that had two functional groups, nitrile and carboxylic acid, how do you think you interpret that table to one has to win? Which is higher priority? So the root molecule is a carboxylic acid, highest priority. That means everything else gets defaulted as a substituent. The nitrile would now be a substituent, not a main chain one.
Then you would have to number it.
Yes, but that's all, and you have to know what number it. Exactly. Yeah, exactly. Okay. So on this example, how many carbons in the longest chain? So everybody all together, A, B, C, D, or E, it is? Ooh, I got C, and we got A. Yeah. That doesn't feel good, right? No, this is like, wait a minute, you just said the longest carbon chain. Why is this the right answer? Right. So this is the whole point. Remember, make your life easy. If we said, oh yeah, this is easy, I can count longest carbon chain. That's 8 carbons, no problem. All right, let's name this side chain. Oh, what? If your side chain gets complex, like, again, step back. Let's go back over here. No. Different question. What is this molecule? What I mean that by is if you look at this, take a snapshot, you're going to sit there and you saw this molecule on the side of the street. You're talking to your friend later and it's like, man, I saw this was like a really hot. But what category of molecule would you describe this as? This is a alcohol. If it is an alcohol, the longest carbon chain must contain that functional group. If you're modifying the end of that name, it is an alcohol, meaning that is the end of the name, the functional group is associated with it. You have to select the carbon chain that incorporates it. Otherwise, those alcohols are side chains. This would be an octane at that point, okay? So you can violate your longest carbon chain rule as long as it identifies or contains the highest priority functional group. So same thing. What is it in this case? Longest carbon chain is A, B, or C? Longest carbon chain that contains your functional group is A. What is this molecule? What's the functional group on here? Same test. Wow, the other day I was going along and it was this amazing, what did you see? This is a ester. If this is an ester, what makes it an ester is this piece right here. This is the root in that case. There's a 2-carbon piece is the name. That's what became the ester. Everything else outside of that substituent is the substituent to the ester. It's the thing that changed it. Does anybody know what this smells like? Yeah. Yeah. A lot of these esters, I don't know if you guys do the lab anymore. A lot of these small molecule esters are the scents that we have or associate with fruit. So this is actually kind of smells like a banana, a little bit. There's other ones like this, small changes that smell like grape, smell like strawberry. They have a very, very strong scent associated with it. And that's part of the things we use to associate, yes, this is definitely food. There's an interesting part to this too. If I took this molecule here, so I'm going to redraw that. We've got guys like this. If I take this molecule, this is an ester, right? Now, esters over time can react with water. What water does is it gets in between that carbon double bond to oxygen, it breaks it, it inserts it. It's called a hydrolysis reaction. So what you end up making is that and this. These 3 carbons here are these 3 carbons here. You've snipped this in part, we've inserted water. So now the ester has turned into a carboxylic acid and a alcohol. That's the functional group conversions that are possible, which means you can also form esters from carboxylic acids and alcohols. Interesting thing, these small molecule carboxylic acids, does anybody recognize this one? 2 carbons OH, this is what? CH3COOH is? It's acetic acid. What is acetic acid? It smells like? And do you notice sometimes when things go bad, if you've ever had, like, let's say, juice in the corner of your room for a very long time, not only is it alcoholic, but it smells sour? It's fermentation. Your bodies are actually wired where if you have small molecule carbons like this, that's a sign of decomposition or decay. Some of these have really clever names like cadaverine and like putrescine because they smell like death. Your body is actually wired to actually detect at very low levels these small carbon and say, like, watch out. Now, acetic acid, that's fine. We're used to that, no problem. You add a couple carbons, and this stuff smells just rank. And this is why, again, it comes from this, where fruits, signs that say this is good to eat, no problem. But it's a molecular clock that says if you let this stuff stick around, it will hydrolyze and form these things, which are your warning of this stuff has gone bad. Anyway, again, news you can use that didn't involve hiding bodies or making meth. Yes? What would I name this molecule? So I would call this 2 carbons is a ethyl, right? So this is some type of ethanoate. Ethanoate is referring to 2 carbons as a ester. But it's not just ethanoate. What's on the other side of it? This is how many carbons? So it is butyl ethanoate. The side chain over here, 1, 2, 3, 4, that goes in front of the name. Since this is an ester, it is not just eth, it's an ethanoate, meaning it's a 2-carbon ester. Okay? What about this? Not yet. Not yet. Which statement is incorrect? There are 4 esters, there's 1 ether, there are 2 amides, there are 3 alcohols. So, molecular word search. What do you got? Okay. All together, A, B, C, or D, this is? C. C? I agree with you. So, there are 4 esters. I count 1, 2, 3, 4. In order to identify molecules and function groups and complex ones, this is just like doing a word search. Do not look at it and panic. Start on the carbon chain and walk along the bonding structure, evaluating as you go. That gives you a systematic way of moving through the molecule. Second, okay, 1 ether, where is that? Right there. There are 3 alcohols, 1, 2, and 3. There are 2 amides, there is only 1 amide right here. We're missing the other. To have an amide, what is the critical atom that must be in an amide? We got what's that? Nitrogen. There's only 1 nitrogen in this whole molecule. So we can only have 1 amide. Okay, so name it. So, no. So this is how I name things. We have a program, that's where I draw these structures. It's called ChemDraw. You select the whole thing, you go to a drop-down menu, say name structure, right there, and there's your name. Ta-da. So again, emphasis being, anything that has a systematic way of doing it can be turned into an algorithm. So the reason I say this is, again, what's most important as you go through this is to be able to name up these. This is the level of difficulty we expect. It is not about getting so systematically bent into this, because guess what? We have very simple tools to do this. I have a poster on my, I don't know if you guys saw, When I used to broadcast live in my office at home, I have a giant poster. The poster says motivation. On the bottom, in small script, it says, if a pretty picture, a nice saying, makes you feel very good, you have a very simple job, one that is about to be done by robots. That's why I make robots. Point is, this here is what I want you to be able to do. These are the names that will be associated with them. If anybody has any questions or comments, I'm happy to walk you guys through how to do this. So I'm going to take this one up next time. This is another molecular word search about a really important molecule. We will come back to this. I don't want to talk about him now. So, bonding. Bonds are broken down generally into two general categories. We have covalent and ionic, right? The difference between these two, covalent bonds, is when two atoms are sharing electrons between two different centers. Two electrons are what are holding these atoms together. So all of these would be considered not just covalent bonds, but they're considered non-polar covalent bonds. It's meant to associate or say that the sharing of that electrons is equal. In other words, neither of those two atoms is winning in that tug of war. In the case of hydrogen, the two electrons holding those two hydrogens together are about equally distributed. It's not only on one or the other. Same thing with chlorine or anything else through here. Polar covalent bonds are still a sharing of electrons. There's a long time period where the electrons sit between those atoms. The difference is one of those two atoms is more electronegative. It holds on to the electrons harder. So as a result of that, you get this polarization or disposition where the electrons are more often on one center, less often on the other. So as a result of that, what you get is a positive charge or a localization where the charge is more positive or more negative between the centers. All of these ones are centers what we have an electronegative atom next to a less electronegative atom. And because of that, we get this split. These are important because these become handles. Reactions happen because these centers of local positive or local negative can be used as sort of ways in, chinks in the armor of these molecules to allow us to do other reactions. Ionic is our final one. This is the full-on, like if we had a case, something like from the left-handed side of the periodic table, like hydrogen, lithium. Something from the right-handed side of the table, like chlorine, bromine. This is where the propensity for stuff like bromine to want to hold on to one electron to get a nice full octet is so strong, especially paired with something like lithium. Lithium is no more than happy to just give up one of those electrons. As a result, instead of sharing, that's the sort of a mutual discussion where, you know what, you take the electron, I'm happy being positive. I need that electron, I'm happy being negative. They stay as a formal charge that is always negative or positive between those two. One thing I want to point out, though, you may be used to these things, sodium chloride, but get used to seeing stuff that looks like this. If we take a lithium, something from the left-handed side of the table, or potassium, left-hand side of the table, and then oxygen, carbon, those are ionic bonds. They may be drawn as something like OK, because it's Friday, or carbon lithium. They may be formally shown as a discrete bond, but do not let this fool you. Think of this in your mind as O negative, potassium positive. This is lithium positive makes that guy in the center is what? Carbon negative. What type of carbon is this guy here in the middle? This is a, how many carbon neighbors? This is, not quad. How many carbon neighbors? Yeah, this is tert. How many carbons? No, in this whole thing, how many carbons? So this is tert, butyl, lithium.